Hi, so my topic today is F#, and since this is web dev and sausages, more specifically I will show you what Fable is, which basically is a compiler that can take F# and then you can use the F# on the browser. I'm not a big slide guy, so I only have 2 slides, but boy do we have some code that we have to go through. So just stop me when you want to have donuts. All right, so I will first talk a little bit about F#. I will show you some cool features that it has, and all the features that I will show you are features that you can use on the browser with Fable as well. So F# it's a functional language. It has strong typing. It's one of the ML languages, so if some of you know what OCaml is, the syntax is quite close to OCaml. Facebook used to have this recent ML language. It looks like that. The type system is called Hindley-Milner, and that basically means that you actually don't have to give any type annotations to the compiler. For the most part, the compiler actually knows what the types are, so it's the compiler is quite smart. This is getting off. It's a .NET language from Microsoft originally, so you can use. It's quite close to. Is it okay now? Cool. So on the JVM you have Java and then you have Kotlin. C# and F# are quite similar to that. You can call from F# to C# and the other way around. You have the .NET runtime from Microsoft, but you also can target the browser through Fable as well. There is a package manager which is called NuGet. On F# you usually use something called Packet, which is quite a bit nicer than what NuGet is by itself. Nowadays it's not only Microsoft, so there's a foundation behind F#, at least in theory. I don't know what the actual status is nowadays. And as far as the editors go, you can use the actual Visual Studio or you can use the Visual Studio Code. There's a plugin called Ionite, and then you have one from JetBrains as well if you like that bloatware. All right, that was the first slide. Then I will jump into some code, which hopefully works here. Is this big enough? I guess it is. All right. First, I mentioned the type system of F#. So we have some F# code here. Here we defined a function called add1, and then it has one parameter. The idea is just adds the integer of 1 into whatever value we'll give into this function. And as you can see, we don't have any type annotations, but if I look right here, the compiler actually knows that this function will take an integer and then it will return an integer back to me. Also, the compiler, if it doesn't have any literals like you have here, this one, that's how the compiler actually knew that this has to be an integer. In some other cases, for example, here, the compiler doesn't know whether these are floating point numbers or whether they are integers or something else that has this plus operator.
Could that work with strings also?
No, there's a different operator on F# for that. But since I'm here using this function with integers, then the compiler knows that okay, this has to be integers, and then it will give me the signature. Also, for some functions, it doesn't actually matter what the parameters are. For example, in this one, I have a function that makes a tuple out of 2 values, a and b. So the compiler can actually make this function into a generic function automatically, which is called the automatic generalization. So this is what it looks like. The compiler, this function has whatever types they are, and it will return a tuple out of those values. That's what this means. It's a tuple of 2 values, and that's what the compiler will give us. And we can run this. By the way, this is a notebook, so you can make notebooks out of F# code, just as you can make with Python code as well. So it's kind of cool. I actually use quite a bit of this. So this will print 2, and the other one will print 2 as well, since we are adding 1 to 1. And then I have some representation of the tuple as well here. The next cool feature that I will show you out of F# is called pattern matching, which actually is quite nice in F#. It's not on the Haskell level, but it's quite close. So we can match on primitive types. For example, here we have the FISBUS implemented with one match clause. So this function takes an integer and doesn't return anything. It will just print some values. And you can have these cards in the match clauses as well. So this will match an integer when that integer can be divided by 15, and so on. And then if I run this code that I have, I take a list that has numbers from 1 to 10 and then run this function for all of those numbers. It will produce me whatever FISBUS is supposed to do. Of course, F# has union types or discriminated unions, just as any other real language. Here we have a type that is shape, which is either rectangle or circle, and then they have some values inside of those cases as well. And then you can easily match on union types as well. So we have a function here called area, which will calculate the area of any shape that you give. And then we match on the shape type and extract those values out of the different shapes and calculate the area. And if I run this code, it will print me the area of this rectangle and the area of this circle that I have here. So hopefully these are right. I didn't check. F# also has an option type, so you can match on the option. And actually the F# option type is just a union type of some and none, as in many other languages as well. So if I run this code, it will print some options that I have here. So within this option we have a value of 5, and this has some string, and then there's nothing inside of here. So it will extract those values from the options. And it's kind of cool that the compiler actually has made this into a generic function as well, since this in F# means that print any value. So if you look at the function syntax of this function, it takes option of any generic value. And now if I actually change this into, for example, integer, then this code doesn't compile, because the compiler actually checks these things as well, as any other compiler should, but I know that there are some that doesn't. So if I now try to run this, then it will tell me that this is supposed to be an integer. So that's kind of cool. Then we have something called Computation Expressions in F#, which they are also known as the scary M word that you can see behind me. And basically, if you look at what the M word means, this is the famous clause. No, I'm just kidding. I'm not going to give you a Monad tutorial now. But actually, F# has quite a nice abstraction over these things. So a computation expression is basically, hopefully I can get this back. Basically, way to make these make many things easier when you write some program. For example, here we have a computation expression called sequence, and it's a way to make lazy sequences in F#. So if we if you look here, we have a sequence builder, and we can yield values out of here, and it's a lazy sequence. So it could be an indefinite sequence, and we will get values out of it when we try to get something out of here. And the type of the squares is it's a sequence of integers, and right here, here we have the numbers from 1 to 10, but it could be indefinite. And if I run this, it will actually make a list out of this sequence and print those values. And here we have some squares. So this is basically, for example, in Python, you can have generators. It's quite close to that. So this is one example of computation expressions using the keyword yield. And there are many other keywords that you can use in the computation expressions. Here's another one called async. So that's a computation expression where you can write some asynchronous code as if it were synchronous code. So here we are using this let binding, let exclamation mark, which means that I want to get the value that this asynchronous function returns, and then so if I look at this function, which doesn't fit on the screen, it's an asynchronous function, but since I used this let exclamation mark binding, this code looks like if it were synchronous code. So if, for example, in TypeScript script you would use the await thing, but here I only have to add this exclamation mark to actually get the value out of this async thing. And now if I run this code, I will get how many characters the Web Dev and Sausages website has, which is quite a few. It's actually also quite easy to make your own computation expressions within F#. So here we have an example of how to make the famous maybe monad using the option, the builder or the computation expression thing with F#. So we have different keywords within this computation expression. This bind is the let exclamation mark that you just saw. You can return something from the computation expression. You also have return exclamation mark, which I might show you later what it means. But just by defining these three things, we will have our own maybe monad, and we will call it option here. And I have here an example on how to actually use this now. So I have here some computation that might fail. So the division of integers might fail in case I try to divide by 0. And in this case, that function will return none, and then if it's not 0, then it will return the actual division. And using this maybe monad, I can actually use this let binding, which is the one that we defined here, to write this code, and I don't have to care whether any step within this computation actually fails. It will continue for as long as we have some values, and the divide function actually returns me an option, but within this computation I don't have to care that the return value is an option. It will give me the value within that option, or then it will exit out of this computation and it will return none. So I can write the basic business logic quite easily, and I don't have to care if some steps fail. I don't have to have this if else thing. And and it's also visible from here. I call this print integer function, which actually takes an integer. It doesn't take the option of integer. But since I use this binding, then I don't have to care about the option in this case. So if we run the code here, this whole thing will now return me none. So this actually failed since we are trying to divide by 0, but if I change this into 2, in that case, the computation will go all the way to the end. As you can see that this function is now called, and it returned to a value of 2, and the whole computation actually returned me the option which has the value of 2 inside. There is quite a few different computation expressions defined by us by the F# core library. In Fable, there's one called promise, which basically is a way to do promises with this syntax. So we can use the same bindings as with, for example, the async builder, and we don't have to care that this code is asynchronous. It's quite close to the async one that we saw before, but it's you can, and these promises are actually compatible with the browser one. So if you need to call some JavaScript, it's quite easy to use this as well. One more before we actually go into the browser stuff. So type providers are a magical way to get some types without actually defining those types. So I think it's better to show you an example rather than trying to show what they are. So let's say I'm trying to integrate into some API which I doesn't know. In F# I can use this JSON provider, and I will give this JSON provider an example of the API that I have, and in this case I have the GitHub user API, and I will give it an example of the web dev and sausages page. So this is just JSON containing all the information about the web dev and sausages user. And using this provider, I get this GitHub user API type. And actually, the F# compiler is giving me full type of the API on the compilation phase without actually defining any types other than giving the compiler this one example. And now that I have this type, I can load some other users from GitHub. Like I have here, now I actually loaded the web dev and sausages page, and I also loaded Rick's GitHub user page. And if I now run this code, I'm printing something out of them. So for example, here is the name of those 2 users. And I can show you that I have all the things that the JSON has here, and I can use the autocomplete on my IDE to actually find all the stuff that I have. So this is kind of cool. I didn't write anything other than gave the compiler this one example. And okay, let's get the name of these 2 things, and I can run this. It seems like also Rix has some pictures on GitHub, so I can.
Don't show those.
I can.
Oh no!
So I'm showing the Rix avatar URL picture as well here. So these are the names, and this is the handsome man that we have hosting this event.
That was during COVID. Not like that.
Ah, okay. All right. You can do the same thing with databases. So what I have here is a connection to a database on my desktop computers upstairs. And I have some Docker image running some world database. I have no idea what tables are inside that database. And the only thing that I'm now giving the compiler is a connection to that database. So I'm not defining anything about the tables. The only thing that I define is you have this connection now, and I know the database type. And then I get some magical context out of that database. So let's run this and hope that the Wi-Fi works here.
You have like password and username there.
Yeah.
And some hackers in the audience.
This uses VPN, so hopefully you can get in between us and the you can see the username. This is some example database. And now that I have this database, I can actually, there's another computation expressions on F# to actually run some queries against some database. And what I have now, there's some scheme inside the database called public, which I suppose is the default. And I can see all the tables inside this database here. So there are some cities, there are some countries on the database. These are the tables and some country language. So let's select the first 10 countries on the database and print them here. So there are some countries on the database, and I have fully typed. I can select whatever I want. These are the columns of the table. So there's population of the countries, some region, surface area, and some other stuff as well. Let's leave the name here. And I can do some more complex queries as well. And it's all fully typed, so I don't have to do anything by myself. The only thing that I gave to the compiler is the connection to that database. And if I run the latter one, I'm here selecting all the cities in the country of Finland. So I'm joining the countries and cities here and selecting some things from the city. So there's Helsinki, Tampere. Helsinki is in Nymaa, which I suppose is how Uusimaa is in English. Oh well. Some example. They also don't know what Tampere is in Swedish. So that are the type providers. So those are some of the F# features that I wanted to show you. Then I have the slide 2 about Fable, and then we can look at some Fable code. Do you have any questions at this time? Or? All right. I can drink in the meantime.
Those type providers were fascinating, but also like bizarre. How would that work in an actual code base? Like now you cannot compile your system if you don't have a database running. Like
on the database case, that might be true. That you have to actually give it the database to connect to. On the JSON case, you can, for example, have local JSON files within the repo and use those as your types. I don't know if you can do something similar for the database. I'm not sure.
Is it simple to write your own type provider?
Yeah.
Cool.
We can do that in 1 hour upstairs. It's surprisingly easy actually. Anything else? Or should I go into Fable?
Yeah, maybe. Let's not keep it too long.
All right. So Fable it's just a compiler, the F#. You can compile into ES6. Most of F# is supported, and many .NET libraries as well. It's quite easy to call JS from JS and to JS. So, especially if you compare to what Elm has nowadays. And then within those same packages, you can actually have the Fable bindings, which basically is just the source code of any library, and then the Fable compiler can actually compile that into JavaScript. And these packages can also depend on NPM packages as well, so you don't actually have to use NPM yourself if you don't want to. So that's at least for me, that's kind of cool. All right, let's look at some Fable project. So, oh my. Like half of this is visible. So I have the famous to-do application running here on my computer running Fable. I can first show it to you. Hopefully it's running. So this is just a basic to-do application. We have some to-dos that we can add, and then it will add them into the server and get the result back. And what I have here on the F# side, I have these 3 projects within this one project. So I have some common code, and that is some code that are used both by the server and the web UI, and then I have the server and the client. And we can actually first look at the common code. Let me close that. So what we have here are some types for the DDOs between the server and the web UI. And then we have some common functions. And this is the interesting part. We have some type here that defines the API between the backend and the UI. So we have, whoops. So hopefully this comes back. All right, so we have 2 functions here defined in this API. We have some function to get a list of to-dos, which is an asynchronous function, and we have some function that you can use to add a to-do, which is an asynchronous function as well. So that's all that is defined as common code. Then we can look into the server implementation. So we have some in-memory storage here for the to-dos. That's not interesting. We are adding some to-dos when the server starts. Not interesting, but this is the interesting part. We actually now have those 2 functions implemented on the server side for adding those to-dos and then getting all the to-dos from the server. And this is using the async computation expression as well. So we just use the in-memory storage to get those to-dos or try to add a to-do. And that's all the implementation that we have on the server side. Then we can use some black magic to actually get a web application out of those 2 function implementations. And that's all that we have on the server side. So we don't have to care about the routing or any other serialization or any other stuff that we maybe don't want to do ourselves. And then if we look at the web application side, this is using something called Elmish, which is quite close to the Elm architecture, if you know what that is. So we have some model on this UI which has the list of those to-dos, and then we have the input, text input from the UI as well. In the Elm UIs, you have some messages that the UI has. So, for example, here we have some set input message that comes from the text input, and it has this string inside. And this will mutate the UI model state based on this string inside. And at least for me, this is the interesting part. We are here using the same type that we defined in the common code and actually getting some kind of proxy from the server, which then we can use that to call those 2 functions within the API just as if they were a local functions right here. So this is all the API stuff that we have to do on the UI side. So if we look at the reducer of this UI, which is called update on Elm, it's basically a function that gets some message and the current model, and then it will change the model according to that message. So I don't know what is breaking. This is at least attached. But could it be on that side? All right, just one more thing. So here we are calling the add to do function through this to do's API, and then that's all we have to do that one call over the network to add that to do on the server side. Other than that, it's a basic React UI. It might look quite strange since we have this F# DSL to actually define these components, but it looks like F#. So this is the UI part. And I will show you one more thing, and then you can get to the donut. So if we actually look at how this looks on the network tab, since we didn't define any routing or any way we want those messages to be serialized, let's see how F# is actually doing this. So if we open the network tab and then try to find the UI underneath, if I now add something here, it's calling this add to do endpoint on the server, and it's using the type name as the route and the function name as the suffix of the route, and the payload is the type that we defined in the common code, and it's doing everything by magic for us, and we don't have to define anything by ourselves. So it's kind of cool what you can do when you have single language on the code base and all this black magic that the F# compiler can give you. It's quite enjoyable. I can stop here, and if someone has any questions, then I can try to answer.
Lots of black magic there.
Yeah.
Yeah. Thank you. Is there any questions?